Hello friends, welcome to the fifth video lecture of the series, and as I promised that we'll discuss some problems, so here we are with this new and different numerical. So before starting or solving any numerical, we should always analyze it before, right? So what you can see is that beam is there which is supported by a roller support at one point and the pin support at the other point, and some kind of external loading is there. Now these loadings look different, right? So are they going to behave differently? Well, we'll answer your questions in the preceding sections. So, moving forward, this is a given data, or you can say that these are the known conditions for this beam. So, 2 kilonewton load is applied at point. So, this is the concentrated load which is acting on point A. And between point B and C, load is varying. So, what you can infer from this is that from point B to C, uniform varying load is acting, whose intensity is varying from 1 kilonewton per meter to 3 kilonewton per meter, right? So this was all about external loading. Now point B is roller joint and point C is pin joint. So due to these external loadings, reactions will come on point B and C. So our aim is to find the reactions at support B and C, and then we'll find the forces and moments at point D in the beam to finally conclude that how our beam is going to behave. Okay, so let's start our journey. Uh, Now, in order to find the reaction forces and moments, first thing we need to do is to replace the support by its reaction equivalents and then draw a free body diagram of the whole structure. So let's see that what are the reactions present on the structure. So, yeah. So these are the reactions. At roller support, we are going to get one perpendicular reaction, that is the reaction in y direction. Similarly, in pin support, we are going to one horizontal and one vertical reaction, right? So before proceeding to the equilibrium condition, what you can see is that for UVL, that is uniform varying load between point B and C, load is not concentrated at a single location. So here is a small trick using which you can simplify these steps required. Well, thanks to the equivalent loading concept, that we can replace this distributed load by its equivalent concentrated load and concentrated moment about any point in the structure. So to understand this, let's review the equilibrium conditions again. So it says that the summation of all the forces and moment must be zero, but it doesn't talk anything about distributed or concentrated load. So for explaining this, let's take a simple case of a uniform distributed loading with intensity F. See, this is uniform distributed loading because here intensity is uniform from starting to ending. In the question that we are discussing, it's uniform varying loading because our intensity is varying. Okay, it's easy. So now if you take a force balance, so if its intensity is F, let me mark this thing. So its intensity is F Newton per meter. Okay, F Newton per meter is the intensity, and if the loading here, the length is L, right? So what you can say, what is the total force acting on this beam is F into L, right? So now if you take a force balance, we can see that the sum of reactions must be equal to the integration of force along the length, which is equals to F into L. So these will be our reactions, that R1 plus R2 minus of integration of 0 to L f dx is equals to 0. R1 plus R2 is equals to F into L. So why this negative sign is coming? See, you can now, I think you can conclude these things because reactions are acting in the upward direction and our external loading is in the downward direction. So that's why the signs are opposite. Okay. So what does it mean? This means that this force can be replaced with the equivalent loading of F into L. So is this enough? Well, no, there are some more things that you have to keep in mind. What are those things? Well, we'll see. Yeah, we have to go a little deep into the concept. So first thing what we'll try to find is the value of reaction force at A. So like you can also choose point B, it is just one personal interest. So in order to do so, let's take a moment balance about point B. Now VA are the vertical force at A and VB is a vertical force at B. Now you need to think that why I'm talking about moment balance about B or A, because see, we can take any other point, but there is some reason, there is some particular reason that we are taking the moment balance about point B. Well, just think, and what you'll get is, because by taking moment about reaction point, we are eliminating the variable from the equation. It's easy, right? So yeah, that girl is saying correct. Now we should go and move forward on our reactions. So if we take a moment balance of distributed load, that is the first case, what you will get is VA into L minus integration, because it's a uniform distributed load. The this integration will come as F into L minus X into dx. So dx is any small elemental strip that I'm taking, and F is, again, as you know, here this is F. Okay, I'm giving the same notation that I have given before, Newton per meter. So this is F Newton per meter. So F into L minus X minus dx. So let's say that I'm taking any line here, suppose here. So I'm taking this as a dx. So now your integration, I think now you can write this equation. So when you'll solve and you'll do the computation, what you'll get the value of VA is this thing, like VA into L. So this is what you're going to get in the end. I insist you please solve this thing and get this value. Now, when you'll take the second case, that is when you are concentrating our uniform distributed load at a point, what you will get is this thing. It is quite simple. This is VA into L, which is acting in the clockwise direction, minus F into L. See why it is F into L? Because now you have concentrated it, right? So it is F and this length was L. So this force will be F into L. Okay? This length was L, right? This length was L. That's why this force is F into L, which is acting at a distance of L minus X is equals to 0. So when you will solve this thing, what you're going to get is this equation. Okay, I'm highlighting this equation. So just pause and try to solve these equations and see if you're getting these equations or not. Okay. Now we need to compare these two equations. So if we are going to compare it, let me remove these. Yeah. So if we compare the two equations, they are going to be equal. Well, where is my first equation? Yeah. So these are my two equations, and when I'm going to compare these two equations, or when you are going to compare these two equations, they are going to be equal only and only when x is equals to L by 2, right? And which is also the centroid of load distribution. So to investigate it further, just compare the two equations and understand the difference. See, now after comparing, we'll add a constant value to the right hand side of the equation 2, such that it becomes equal to equation 1. Then mathematically both equations become equivalent. Now what is that constant value? That constant value in terms of mechanics of material is called a moment. So we can apply equivalent loading at any point, but the only thing is, when application of loading is centroid, there will be no moment. I hope now it is clear, because when it is L by 2, there will be no moment, but when, like, I have taken at a distance of x, so at a point at a distance of x, when it is not equals to L by 2, one load and one moment will come. Okay, so the value of C will be equals to F into L into x minus F L square by 2. Now I think that I've explained too much of the numerical problems, so I think we should start our problem and start implementing what we have learned today on this problem. Okay, this was the case of example that I have given as a uniform distributed load. So now we'll go back to our numerical that was of uniform varying load, and we'll implement whatever we have learned right now. Well, I can give you one hint here, that not hint, just I'm telling you that concentrated force is the area of distributed force. So for this numerical, what will be the area? Yeah, it will be an area of a rectangle and a triangle, because when you're going to divide this UVL, you'll get one rectangle and you'll get one triangle. Also, what is the centroid of a rectangle? It is at a distance of L by 2 from either of the sides, and similarly for triangle it will be at a distance of L by 3 from the bottom. Okay, so that means when you will concentrate the load of rectangle, it will act at a distance of L by 2. Similarly, when you will concentrate the load acting of like triangle, it will act at a distance of L by 3 from the base. Okay, so now we should start working on our equations. So this was a problem. Reactions are shown, everything is shown, marked, done, perfect. So now we'll write the moment. We'll take a moment which is we are taking about point C. Okay, I have marked the 2.4 kilonewton and 2.4 kilonewton. They are the what I have converted from UVL to concentrated load. Okay, so when you'll do a moment balance about point C, you can assign any force, any clockwise or anti-clockwise moment to be positive or negative, because in the end we are going to get the same answer. Okay, so I'm starting and I'm taking anti-clockwise moment as a positive. So this 2 kilonewton, the load acting on point A, will give an anti-clockwise moment which is at a distance of 1.6 plus 2.4. Similarly, our VB, wait, let me mark these things. Yeah, here, see this A is going to give in this direction. Similarly, this VB, it is going to give in, this is a VB, right? So this is going to give in other direction. Similarly, 2.4 kilonewton and the other 2.4, they are also going to give a anti-clockwise direction. And this is the reason why only this is having negative sign and all other are positive sign. So when you solve this, what you'll get is, you'll get the value of VB, which is equals to 5.33 kilonewton. So just pause the video and see whether you're getting the same value or not. And if you're not getting, that means you have done any sign convention mistake or any, mathematical mistake, nothing else. So moving forward, we have done the moment balance. The next is our force balance. Now you know VB. So what is left is you need to find the vertical reaction at point C and the horizontal reaction at point C. So when you do the force balance, what you'll get is VC plus VB, that is the reactions in the upward direction, is positive, minus all the loads acting in the downward direction, that is 2, 2.4 and 2.4 equals to 0. So after solving, you will get the value of VC as 1.47 kilonewton. Now what is left is force balance in X direction, that is in horizontal direction. But as you can see that there is nothing acting in the horizontal direction. So our HC will come as a 0 kilonewton. So we have found all the reactions at point B and C. So done. So our second part was to find the movement and the force at point D. Okay, so what we have to do is simple. We have to mark our forces, mark our movements, and take a free body diagram and solve just the equilibrium conditions. So now you know that we know the here VB. We know what is the value of VB here. So first we'll do the force balance, in which summation of forces in X direction is 0. So again you'll get HD as 0. That means horizontal force in that point D is 0. So when you do the force balance in the vertical direction, now VD is acting upwards. Similarly, then 2, 1.2 and 0.6. Now see, just think that why I'm taking 1.2 and 0.6, because I'm only concentrating the UVL that is before point D. That's why I'm not getting the 2.4 and all, right? So you have to do a little bit of maths here. And so what you will get is the value of VD, and after getting value of VD, you need to take a moment about point D and solve, and you'll get the moment at point D. So the only catch that was here was that if you are taking any point, so when we are cutting the free body diagram, we are taking at point D, your values of concentrated load that you are getting from UVL, that is uniform varying load, will change. Okay, so when those values will change, because you are considering only the portion that is before D, so you will get the answer. Okay, so this was all about this numerical. If you like the video, please subscribe for more interesting videos. Thank you.